In this video, I'm going to show you a trick, this theorem, for finding the volume or surface area of a solid of revolution. And so we're going to start by actually doing a refresher of how we find the centroid. So we proved this in class, so we're just going to write it down here. The centroid of this region, and again, that's like where this little, it kind of looks like a whale in this picture, but it's basically like where we think it would balance if we were going to put it sitting, like imagine trying to balance it on the tip of a pencil. So I'm guessing maybe it would balance right around there. That's our x bar, y bar. And so in class, we showed that this is going to be the same as the moment about the y-axis over the total mass. And this is going to be the same as the moment of the x-axis over the total mass. And assuming that I want the centroid, centroid means the center of mass of a region of constant density. Okay, so we can assume that rho is constant, and then we actually derived each of these parts in class, m sub y, m sub x, and my total mass, so let's just jot those down. Okay, so here was the x location of the center of mass, and because my density is constant, we can pull it out front, and it'll cancel. And then notice in the denominator, we just have the area of the region. So another way I can write this whole thing is as this. And then we can do a similar thing with y bar. So let me just create some room here. So my denominator is still going to be the same as what I had, my mass, and then notice you'll be able to pull the density out. And then my numerator is given by this, and again that was derived in class. And so again we can simplify this to 1 over the area and then just times what I have in the numerator. Okay. Now, so how can we use this? This so far only has giving us information about the centroid. How do we use this to help us figure out volume or surface area? Okay, so now B, let's suppose we're going to take this little whale-looking region and we're going to rotate it around the y-axis. Okay, so this is going to be our rotation. We know how to do this, so take this for a minute, set it on pause, and see if you can set up using shells what the integral would be to find the volume of that solid of revolution. Okay, so if you recall, using shells, cylindrical shells, you're going to take a slice here, and that was like the little piece of the edge of the toilet paper that I had us imagine, and then you're going to pull that whole roll around the y-axis, and so you can see that your radius is just going to be x, and the height is going to be f minus g. So your total volume is going to be, r is just going to be x, and then your height is just f minus g. But now I want you to notice, look above at the centroid integrals that we found, because this integral here looks really close to the integral that we have for the x component of the centroid. So see if you can take a minute to see what you need to do to rewrite what I have down here in terms of x bar. Put it on pause. So notice I can pull out the 2 pi from here, and then I'm left with the exact integral that's in the numerator up here, which means I can multiply both sides of this up here by the area, and I would be left with the integral that I wanted. So down here I'm going to have 2 pi times x bar times a. And that's going to have to be the same as the volume that I'm looking for. But now notice 2 pi x bar, well, that's just going to be the distance that the centroid is going to travel during one rotation around the x-axis, because that's just going to, think of just creating a little circle, and you want the circumference, and your radius is just x bar. How far is that centroid going to travel? So this is the same as taking the distance traveled, d, of your centroid in one rotation times the total area, d times a. And that's all you need to do. That's the trick. So now use this. You notice you don't even have to do an integral in this case. You can just simplify it to this 2 products. So we can use this now to go back to the torus that we've done in class and find that volume really quickly. Okay, so here's the torus we've looked at in class, and we found this volume 2 different ways in class. And now we're going to redo this. We found it using washers and then also using shells, but now I want you to redo this using the theorem of pappus. So put this on pause and see what you come up with. Okay, so first the area of this is just going to be pi r squared, but you can see my radius is just 1/2. The radius, I'm just looking at this circle, so just like this radius right there. And then the distance traveled by the centroid. So notice the centroid is going to be right at the center of the circle, so right here at 1, 0. And then in one rotation, so you can just imagine it's going to get rotated around the y-axis, and it's going to create this little circle here. And that circle is going to have circumference 2 pi r, where my r is the distance from the centroid to the y-axis, which is just going to be 1. So we're going to get at the end that the volume, just like we got before, is going to be pi squared over 2. But notice we didn't have to do any integrals once we're using the theorem. So by similar reasoning, you can actually show that if you want the surface area of a region of revolution like this, that it's going to be given, instead of doing the area times the distance traveled, which is what we did to find the volume, now to find the surface area, we're going to take the arc length of the generating curve, and then again times the distance traveled by the centroid in one revolution. So in this case, my generating curve is just this circle here, and so we know that its total arc length is just going to be 2 pi r, where my radius here is 1/2, so 2 pi r, that's this piece. And then the distance traveled by the centroid, so notice the centroid itself, if you think of rotating this thing around, the centroid itself is not contributing to the surface area that we're calculating. However, you would still just imagine what's the total distance traveled. So it's going to be the same thing that we had before, 2 pi, and now my radius is just 1. Okay, so for this particular torus, the surface area is going to be 2 pi squared. And we can get that again the long way doing actual integrals and using the surface area integral, but this is using nice properties of the centroid, and it's a nice quick way for you to check your integrals.